Flight planning is an important activity of every pilot. A critical element is careful consideration of the airplane performance capabilities for the airports used for takeoff and landing. This is especially true for the takeoff, since the airplane is often near its performance limiting weight. Every pilot is aware that the length of runway available for takeoff significantly influences the maximum allowable takeoff weight. But what lies beyond the runway may be of equal significance. Planning for takeoff obstacle clearance in transport category airplanes. Obstacle clearance is an important element in transport category airplane performance planning. This module will review the relevant certification rules, the operating rules, and FAA guidance for assessing takeoff obstacle clearance in transport category airplanes. Takeoff obstacle clearance planning often presents its greatest challenge at mountain airports. The airport at Aspen, Colorado, located in the Rocky Mountains, serves as an excellent example with which to explore this challenge. Let's listen in as a flight crew briefs their flight plan from Aspen to Atlanta, taking into consideration one engine inoperative.
I would think the first thing we need to look at is the runway out of Aspen. So I have that right here. And taking a look at the runway, it looks like it's 8,006 feet long. But there is a displaced threshold, so let's go see what that's all about and make sure there's no limits there. When you look at the numbers right there, it says the last 1,000 feet is not available for landing distance computations in the note. Well, we're not landing there, we're taking off, so that's not going to be a huge issue for us. No big deal there. We're also going to be using the lens departure procedure, and it has weather minimums on it, which are, I believe, 400-foot ceiling and 1 mile visibility. Is that correct?
That's correct.
Okay. And a minimum climb gradient. Do you have any questions about that?
I don't think we're going to be able to meet that climb gradient single engine.
No, we won't. 2-engine, not much of a problem. We can look that up and verify it. But 2-engine, we can meet it. Single engine, we won't. So we're going to need another plan.
This flight crew has accomplished a thorough review of the performance challenges affecting their planned departure from Aspen. Now let's take a moment to examine the challenge of takeoff obstacle clearance and avoidance planning when departing Aspen. A review of the certification rules regarding the takeoff path is a good place to begin our discussion. The certification rules define a takeoff path or vertical profile that is used to establish both the takeoff climb limit weight and the takeoff flight path for determining the takeoff obstacle limit weight. The takeoff path is divided into a series of segments. Let's examine each of these segments in greater detail. The takeoff path begins from a standing start. The critical engine is failed at VEF and remains inoperative for the rest of the takeoff. The first segment begins at liftoff and continues until the landing gear is fully retracted. The airplane is accelerated in the air to V2 speed. During this segment, a turbine-powered airplane with 2 engines must be capable of achieving a positive climb gradient in still air with 1 engine inoperative and without the benefit of ground effect. Additional climb performance is required for airplanes with more than 2 engines. The second segment begins once the landing gear is fully retracted. The airplane must once again demonstrate a minimum climb gradient in still air with 1 engine inoperative. For a turbine-powered airplane with 2 engines, that minimum climb gradient is 2.4%, which is determined at the point where the landing gear is fully retracted. Additional climb performance is required for airplanes with more than 2 engines. The first and second segment climb is based on flying V2 speed. However, it is important to understand the significance of this speed. If the engine fails at the most critical point in the takeoff at VEF, which is reached just before V1 speed, and the pilot, electing to continue the takeoff at V1, rotates into the target engine failure takeoff pitch attitude, the airplane will attain V2 speed at the point that the airplane attains a height of 35 feet above the runway. If the engine failure occurs above V1, many AFM procedures recommend rotating to the same target pitch attitude. As a result, the speed obtained at 35 feet will be higher than V2. These procedures recommend maintaining this higher speed up to a maximum of V2 plus 10 to V2 plus 20 knots, when such an increase does not affect climb performance. The second segment must continue to a minimum height of 400 feet above the runway surface. No changes are allowed to the airplane's configuration or thrust while maintaining a speed not less than V2. The climb gradient during the second segment will gradually diminish due to thrust decrease resulting from increasing true airspeed and reduced air density as the airplane gains height. Therefore, the climb gradient capability will be greatest at the beginning of the second segment. Once the airplane has achieved at least 400 feet above the runway surface, the transition segment may begin. During this level flight segment, the airplane is accelerated to flap and slat retraction speed, and then to the final takeoff airspeed. The transition segment ends when the airplane is in the clean en route configuration, at an airspeed of not less than VFTO, and when the remaining engines are set to maximum continuous thrust. If the airplane is less than 1,500 feet above the runway surface at the end of the transition segment, then the final takeoff segment begins at that point and extends until the airplane reaches at least 1,500 feet. At any point above 400 feet, a turbine-powered airplane with two engines must be capable of achieving a minimum climb gradient of 1.2% in still air. Additional climb gradient capability is required for airplanes with 3 or 4 engines. Over the years, the airspeed flown during the final segment has been referred to by a number of different terms. You may be familiar with VFS, VENR, or VSSE. In 2002, FAA incorporated the term VFTO, or final takeoff speed, into the certification rules to identify the airspeed to be flown in the final segment. This speed provides an adequate margin above the stall speed in the clean configuration. Here we see the complete takeoff path from brake release until the minimum height of 1,500 feet above the runway surface. It is helpful to think of these minimum climb gradients imposed by the certification rules as a mandatory minimum level of the airplane's surplus energy condition during takeoff. This surplus energy can be used for either climb or acceleration, or some combination of the two. Since these climb gradient requirements are based on airport temperature and pressure altitude, they are not runway specific. However, choosing flap settings for a given takeoff can affect the climb limit weight. Increasing flap settings used for a takeoff reduces the runway length required for takeoff in most cases. However, it also decreases the takeoff weight limit at which these minimum gradients can be achieved. Depending on the runway choice available for takeoff, this interrelationship effectively means that the climb limit weight may be runway specific. These climb gradient requirements are intended to provide a minimum acceptable level of one-engine-inoperative climb performance, but are definitely not intended to satisfy obstacle clearance requirements. Obstacle clearance must be considered separately. The requirements for takeoff obstacle clearance may be found in Subpart I of Part 121 and Subpart I of Part 135 of the Code of Federal Regulations. Looking back at the operating rules for an airplane like the DC-6 or Lockheed Constellation, following an engine failure on takeoff at V1 speed, the airplane was required to clear obstacles by 50 feet at any point until the airplane's actual height above the runway was 1,000 feet. In the 1950s, it was recognized that 50 feet of obstacle clearance after an engine failure was not sufficient to support the new generation of jetliners that were on the horizon. To provide adequate obstacle clearance for the new turbojet airplanes, the air carrier operating rules introduced for these new airplanes in 1957 provided an increasing margin of obstacle clearance as the airplane traveled further from the end of the runway. To provide this obstacle clearance margin, these new rules required that the takeoff path clear any obstacle by 1% of the obstacle's distance from the end of the runway plus 35 feet until the airplane was 1,000 feet above the runway. These rules proved cumbersome for operators to use and were quickly modified. As a result, they were applied only to early Boeing 707s. Beginning in 1958, the certification rules defined a separate takeoff flight path that begins at 35 feet above the runway surface at the end of the takeoff distance. It is a one-engine-inoperative path that continues through each of the takeoff segments and ends when the airplane is at a height of 1,500 feet above the runway, or at the point at which the transition to the en route configuration is complete, whichever is higher. This actual or gross takeoff flight path represents the one-engine-inoperative performance that the airplane has been demonstrated to be capable of achieving for a given weight, thrust configuration, and set of environmental conditions. To simplify the obstacle clearance analysis process, these revised certification rules also defined a new net takeoff flight path. The net takeoff flight path is determined by decreasing the airplane's demonstrated one-engine inoperative performance by a conservative margin. When required by the operating rules for turbine-powered airplanes, this net takeoff flight path must clear obstacles by 35 feet. For four-engine airplanes, the net takeoff flight path is defined by reducing the gross climb path by 1%, thus retaining the original 1% obstacle clearance margin required by the previous operating rules for the Boeing 707. For the level acceleration and flap retraction segment, the 1% regulatory gradient reduction is converted to an equivalent reduction in acceleration, resulting in a net third segment that is longer than the gross third segment distance. For three-engine jet airplanes, the regulatory gradient and acceleration reduction defining the net takeoff flight path is 0.9%. For two-engine jet airplanes, the regulatory gradient and acceleration reduction is 0.8%. Clearing an obstacle by 35 feet doesn't sound like much of a safety margin, but remember that the net takeoff flight path is defined as the actual flight path, often referred to as the gross path, minus the prescribed reduction in performance. The intent of defining obstacle clearance in terms of net performance is to provide a reasonable safety margin should the airplane's climb performance following an engine failure be less than predicted. These differences are due to the operational variations that can reasonably be expected in gross weight, thrust, airplane drag, pilot technique, wind effects, and so on. However, except during the level flight segment, there will be an increasing margin of obstacle clearance between the actual takeoff flight path following an engine failure and the net takeoff flight path used to assess the required obstacle clearance. For example, if a two-engine airplane is 10,000 feet beyond the start of the takeoff flight path at 35 feet during the second segment climb, the difference between the gross height and the net height will be 0.8% of 10,000 feet, or 80 feet. Thus, the requirement that the net takeoff flight path must clear the obstacle by 35 feet means that the airplane will actually clear the obstacle by as much as 115 feet. As noted previously, variables that may reasonably occur during normal operations may reduce this margin. The takeoff flight path and net takeoff flight path begin at 35 feet above the runway surface. For airplanes with FAA-approved wet runway takeoff data, this can result in lower than normal obstacle clearance in the event of an engine failure on takeoff near V1. Because the airplane is allowed to be at a height of 15 feet above the runway surface at the end of the one-engine inoperative takeoff distance for a wet runway, the airplane can be 20 feet closer vertically to the obstacle after taking off from a wet runway compared to taking off from a dry runway. Of course, if there is no engine failure during takeoff, there is no difference in the flight path of the airplane taking off from a wet runway compared to taking off from a dry runway. The airplane manufacturer is required to furnish performance data and procedures for use in assessing net takeoff flight path obstacle clearance. The airplane manufacturer has significant latitude in the design and presentation of this data, including providing it in an electronic format. In addition, the procedures used for constructing the net takeoff flight path and the nomenclature used on the data charts may vary widely between manufacturers. While the complex array of charts typically provided in the airplane flight manual satisfies the regulatory requirements, most pilots would find it impractical to use these charts for routine departure calculations. The days of pilots calculating takeoff obstacle clearance from pages of paper charts in transport category airplanes are long gone, and for good reason. Today, the options furnished by the manufacturers to optimize the performance capabilities of these airplanes are very complex. The obstacle data sources that must be considered have grown in number, as well as the sheer number of obstacles that must be considered in any net takeoff flight path analysis. It is no longer considered feasible or practical to expect pilots to determine a takeoff weight limit for obstacle clearance on their own. Rather, it is expected that the analysis is completed by a professional aircraft performance engineer or a performance engineering provider, with the necessary training and resources available to make full use of data provided in the airplane flight manual. In addition, they are expected to collect and maintain an obstacle database using the best and most current data sources available for use in performing the analysis. In many cases, electronic performance data is now being provided by manufacturers, and in some cases, the flight manual performance data is no longer provided in paper form. Performance engineers will most often use the airplane flight manual data to create a more practical means for pilots to evaluate obstacle clearance to support flight operations. Examples might include a software performance calculation tool, such as might be installed in an electronic flight bag, or a runway-specific airport analysis, summarizing the limitations for departure from a given runway. However, even these tools are dependent on a properly maintained obstacle data set. Regardless of how the analysis is prepared and presented, there are a few important items that all pilots should know about the net takeoff flight path obstacle clearance analysis. The airport runway analysis prepared by the performance engineer provides the pilot with the maximum allowable takeoff weight in consideration of performance requirements for the takeoff airport and runways specified. Because the climb weight limit is not directly associated with departure from a specific runway, it is often shown in a separate location from the runway weight limit. In addition to the climb weight limit, a runway weight limit for each runway is provided on the analysis. The runway weight limit considers each of the performance requirements that may restrict maximum allowable weight when taking off from a specific runway. Among other things, this runway weight limit assures that the net flight path will clear all identified obstacles by the required margin along the departure path. When preparing the analysis, the performance engineer must consider the performance data and procedures for calculating the net takeoff flight path prescribed for each airplane type. The net flight path data for most airplanes allow a second segment climb to any height above 400 feet that is necessary to clear obstacles up to a maximum height that permits the cleanup and acceleration to VFTO speed to be completed within the time limitation on the use of takeoff thrust. For those runways where obstacle clearance is not a limitation, the operator often establishes a standard acceleration height, for example, 1,000 feet above the runway elevation. The acceleration height is provided on the airport analysis for each runway end. Leveling at this height may be required for obstacle clearance in one of the takeoff flight path segments. However, on some airplane types, the second segment net takeoff flight path data terminates at a gross height of 400 feet above the runway. When this is the case, the engineer must plan the transition segment obstacle clearance on the assumption that the pilot will level off and accelerate at that height. Therefore, the maximum allowable takeoff weight cannot be based on climbing higher than 400 feet above the runway. Still, other airplanes are capable of an extended second segment climb, where the airplane is assumed to continue climbing at V2 with takeoff flaps to the end of the takeoff thrust limit. The transition segment is then completed using maximum continuous thrust. To use this option, it must be demonstrated that the airplane is capable of meeting the minimum gross climb gradient requirement for the final segment at the designated acceleration height with takeoff flaps extended and maximum continuous thrust. Using data furnished in the AFM, the engineer determines weight limit additions or subtractions applied to the runway limit weight to account for headwind or tailwind component, non-standard atmospheric pressure, engine bleed and ice protection configuration, and so forth. In some cases, the corrections are tabulated as part of the airport analysis, and the flight crew must apply adjustments to the limit weights. To deal with the complexity of the obstacle clearance analysis, some pilots have tried to simplify it by thinking of it in terms of meeting a required climb gradient. For example, the standard 200 foot per nautical mile or 3.3% climb gradient used on IFR departure procedures. It is important to understand that the one-engine-inoperative climb gradient data furnished in the airplane flight manual represents a spot value or snapshot of the airplane's performance at a particular point in the takeoff path. Airplane climb performance diminishes as the airplane climbs due to thrust lapse rate loss and as true airspeed increases with height. While it may appear that acceptable obstacle clearance can be demonstrated using a rise over run analysis based on a spot climb gradient, in reality, that is not the case, since the first and second segment net takeoff flight paths are not a constant gradient. As we just mentioned, the gradient reduces as the airplane climbs due to thrust lapse rate loss and as true airspeed increases with height. In addition, there is often a marked difference in slope between the first segment and the second segment due to drag resulting from the landing gear retraction sequence. Typically, the only rise over run obstacle assessment found in the AFM is for the final segment. The final segment flight path does not have any large discontinuities in it since the configuration is constant throughout, unlike the initial portion of the takeoff flight path where the gear is in extended position in the first segment and in the retracted position in the second. The combination of these factors make it possible for determining a conservative gradient based on the distance to the obstacle for use in a rise over run obstacle analysis from the end of the transition segment through to the end of the final segment. As you can see from this graphic, a simple projection of a climb gradient does not ensure compliance with the obstacle clearance rules in the event of an engine failure. Any time that the yellow line showing the constant assumed net second segment climb gradient is above the red net takeoff flight path line, we cannot assume that the constant gradient method will provide the required obstacle clearance because it does not reflect the airplane's true net takeoff flight path. Our discussion thus far has focused on how the net takeoff flight path clears obstacles by the required height, but we haven't discussed which obstacles must be cleared. To help answer this question, FAA released Advisory Circular AC 12091, Airport Obstacle Analysis. According to the operating rules in Part 121 and Part 135, any obstacles that are located 200 feet on either side of the flight path within the airport boundary, or 300 feet on either side after passing the airport boundary, must be cleared vertically by the net takeoff flight path. This advisory circular, released in 2006, provides guidance on developing obstacle analysis that meet the intent of this requirement by accounting for factors that may cause a difference between the intended track of the flight path and the actual track of the flight path following an engine failure. The AC provides methods that account for factors that may affect the actual ground track relative to the intended ground track, such as wind and available course guidance. This is accomplished by using an obstacle accountability area within which all obstacles must be cleared vertically by the net takeoff flight path. For an engine failure procedure that is centered on the extended runway center line, this area begins at the runway end and expands at a predefined rate until it is at a maximum width 2,000 feet either side of the intended track. For some runways, a straight-out engine failure procedure may not be possible or desirable in terms of maximum allowable takeoff weight. On these runways, a special engine failure procedure may be provided that takes the flight path of the airplane away from the terrain or obstacles that limit the allowable takeoff weight. The turn procedure is computed taking into account the climb speed and bank angle used following the engine failure. The effect on climb performance resulting from the bank angle flown during the turns is included in the allowable takeoff weight limit. Because a turn is involved, the obstacle accountability area expands in width to 3,000 feet either side of the track. The procedure may be defined in simple terms of turns and headings to fly following an engine failure. Ground-based nav aids are usually used to identify the point at which a turn is to begin. Oftentimes, it is beneficial for the engine failure procedure to coincide with the IFR departure procedure used for that runway. The engine failure procedure for Aspen's runway 33 is based on the LIN's standard instrument departure. The major difference is that the turn points are expressed as geographical references instead of crossing altitudes. In addition, this procedure includes a holding pattern at LIN's intersection that allows the airplane to climb to a safe altitude and reach the IFR en route structure. Although not used in this example, there is an option to reduce the obstacle accountability area through analysis of the ground track taking into account wind and available course guidance. Another option provided in the AC uses visual guidance to avoid obstacles. While this may sound simple, the AC requires that specific procedures be provided to the flight crew along with any weather or lighting requirement necessary to maintain reference with the desired ground track. IFR procedures like the LIN's standard instrument departure often contain minimum climb requirements. As mentioned by our flight crew in the Aspen briefing, this SID has a climb gradient requirement of 465 feet per nautical mile, up to 10,000 feet MSL. Over the years, pilots have asked many questions concerning the climb gradients published on SIDs and obstacle departure procedures. They have heard a variety of answers, some of them quite dubious. Let's answer the most important question first. All IFR departure procedures are based on normal airplane operation and assume that all engines are operating. Compliance with the climb gradient published on a SID or ODP is based on the normal all engines operating climb performance of the airplane. There is no requirement to demonstrate compliance with a SID or ODP based on one-engine-inoperative performance. If an engine fails on takeoff in a transport category airplane, the operating rules and procedures previously discussed are used to address that failure. The IFR departure procedure is no longer applicable. The pilot should refer to the engine failure contingency procedure for the runway in question. This procedure was developed to address this specific failure. The climb gradient published on a SID or ODP is treated as a plane, originating at the end of the runway, that must not be penetrated from above until reaching the published altitude, as opposed to a gradient, which must be exceeded at all points in the path. The climb gradient will provide obstacle clearance based on the assumption of normal all engines operating performance. However, the climb gradient on a SID may also be established to meet an ATC requirement, such as separation from other airplanes, and therefore may be greater than what is required for obstacle clearance. These climb requirements are determined in consideration of all aircraft that are authorized to use the procedures and the full range of airspeeds that may be flown by departing aircraft. For example, 250 knots below 10,000 feet. On the other hand, the contingencies procedure for an engine failure on takeoff are developed based on the demonstrated performance for a specific airplane type. The airplane's flight track can be accurately predicted based on the actual speed flown following an engine failure, for example V2 speed. Therefore, as we have seen, the area in which the obstacles that must be assessed for net takeoff flight path clearance is smaller than the area used for normal IFR departures. The flight management systems on many business airplanes provide features for computing airplane performance, including climb weight limitations. Pilots should be aware that the results provided by these systems are only as accurate as the obstacle information entered by the pilot. If the pilot enters the climb gradient requirement published on an IFR departure procedure, the results may be misleading. Hutchinson, Kansas runway 13 has a very simple obstacle departure procedure. Climb heading 132, which is the runway heading to 3,100 feet MSL, before proceeding east. Since no climb gradient is published for this runway, the standard 200 foot per nautical mile requirement is assumed. The FMS for this particular aircraft is capable of computing the maximum allowable takeoff weight based on a climb gradient requirement. The climb gradient we use to determine our maximum allowable weight is the 200 feet per nautical mile standard climb gradient for runway 13 at Hutchinson. We determine our maximum allowable takeoff weight using a typical summer temperature for Kansas, 40 degrees Celsius, which is equal to 104 degrees Fahrenheit. Maximum allowable takeoff weight computed by the FMS for runway 13 is 38,336 pounds. The takeoff field length required is 6,889 feet. Runway 13 is 7,000 feet in length. The declared distances for runway 13 are all 7,004 feet, which is slightly longer than what is shown in the FMS. 38,047 pounds is slightly below the takeoff weight limit. The results returned by the FMS appear to show that we are within approved limits for takeoff on Hutchinson's runway 13. A check of an airport analysis for this runway at 40 degrees Celsius reveals a shocking surprise. The takeoff weight is obstacle limited on this runway to 36,841 pounds, almost 1,500 pounds less than the weight shown by the FMS computation. The answer to this question is found on the obstacle departure procedure for runway 13. Here you will see a list of obstacle notes. These obstacles are tall enough that they would normally require a higher than standard climb gradient. To avoid publishing needlessly excessive high climb gradients to the height of 200 feet or less above the runway, the FAA publishes notes about these obstacles on IFR departure procedures. These notes are intended to advise the pilot of close-in obstacles so they are aware of them and can take the necessary actions to avoid them on takeoff. While these obstacles may not be a significant factor with all engines operating, when required by the operating rules, the airplane's takeoff weight must ensure that these obstacles are cleared vertically by the prescribed amount should the engine fail during takeoff. Here's what the performance engineer would see when checking the obstacle clearance at the 38,047 pound takeoff weight computed by the FMS. The engineer would see that the net takeoff flight path does not clear the obstacle by the required 35 feet and that a steeper net takeoff flight path is required. Here is how it might look to the pilot. Not only does the net takeoff flight path not clear the obstacle by the required amount, the obstacle is very close, less than 35 feet from the predicted actual one-engine-inoperative flight path of the airplane. Hutchinson, Kansas is not an isolated example. A review of the obstacle notes on many IFR departure procedures reveal that the presence of low, close-in obstacles can be a significant limitation on takeoff weight. In addition, there are many other obstacles that are too low to affect the SID or IFR departure procedure standards, but must be considered in the engine-out analysis. As we noted earlier, the climb gradient published on an IFR departure procedure is based on normal all engines operating performance. This often leads to a question: how do I know whether my airplane can meet the published climb requirement? This is not a subject addressed by the certification rules. Therefore, all engines operating takeoff climb performance data is not furnished in the FAA-approved airplane flight manual. As we have seen, there is a requirement to furnish one-engine-inoperative climb performance data in the AFM, but using this data to show compliance with a climb requirement published on the IFR departure procedure is not required by any operating regulation. Some manufacturers may provide supplementary all-engine climb performance data, but if that data is not available, pilots should use their knowledge of the airplane's normal performance capabilities to determine whether they can comply with this climb gradient on a particular takeoff. To aid the pilot with this determination, the U.S. Government Terminal Procedures publication contains a chart that converts the required climb gradient into a corresponding rate of climb value that the pilot can reference during the departure. On Jepeson's charts, this information is published on the procedure chart. The question of what action a pilot should consider or take when the engine failure procedure differs from the IFR departure procedure is worth addressing. At terrain-challenging airports like Aspen, the engine failure procedure typically conforms to the IFR departure procedure for the takeoff runway. However, modifications may be necessary to identify the start of any turns using precise geographical references instead of the altitude crossings that are frequently used on SIDs and ODPs. If it is not already available, it may be appropriate for the operator to request an engine failure procedure that does align to the SID or ODP to the extent necessary for the airplane to reach the IFR en route environment. As we saw at Aspen, this may involve the use of a conveniently located holding pattern. However, some additional pre-departure planning may be required when the engine failure procedure maintains a straight-out track, or if the engine failure procedure differs significantly from the IFR departure procedure. When taking off from runway 9, the San Diego Lindsay SID turns left to a 275-degree heading after passing 4,000 feet. However, the engine failure procedure for this runway calls for a right turn to a 180-degree heading after passing the ISAN 4.0 DME. In this example, if the engine fails prior to reaching 4,000 feet, the pilot is still able to follow the engine failure procedure. On the other hand, if the engine fails after attaining 4,000 feet and in the left turn, the engine failure procedure is no longer applicable. At this point, though, the airplane is above the immediate surrounding terrain. The pilot has any number of good options available. However, it might be wise to think about these options as part of your pre-departure planning. Here are some strategies you may consider applying when the IFR departure differs from the engine failure procedure, or when you expect ATC to provide vectors after takeoff. First, climb as rapidly as practical to 1,500 feet above the airport elevation. Doing so with all engines operating gains altitude quickly close to the airport, mitigating the effects of an engine failure later in the departure. If the engine fails on takeoff at V1, fly the engine failure procedure. If the engine fails during the initial climb out, Fly the engine failure procedure if you are still closely aligned with its track. If the engine fails at this point, the SID or other instructions assigned by the ATC are no longer applicable. When time permits and the airplane is under control, advise ATC of your intentions. Controllers are trained that the pilot of a transport category airplane will utilize a contingency procedure in the event of an engine failure. If the engine fails after the airplane has turned away from the engine failure procedures track, the option of turning back to rejoin the procedure does not necessarily guarantee obstacle clearance. This is where the altitude gained in the initial all engines operating climb is of greatest benefit and provides additional safety. Turn away from known obstacles. Use the terrain display of the TAWS or EGPWS to identify high terrain or obstacles along the current flight track. Use the peaks mode, if available, to identify the height of these obstacles and to assess the need for a turn. The approach chart will portray prominent obstacles, however, pilots are cautioned that not all obstacles are shown on these charts. Finally, seek assistance from ATC. ATC can vector the airplane away from high terrain or obstacles. If necessary, request vectors or a hold from the controller to reduce crew workload while addressing the emergency. When taking off from an airport with limited ATC services or radar coverage, be familiar with the minimum safe altitudes or terminal arrival area altitudes for the approaches serving the airport, especially in the areas encompassing the takeoff and initial climb out. The MSA or TAA for an RNAV approach is centered on the runway threshold. These altitudes provide at least 1,000 feet of obstruction clearance within a particular sector. Once above these altitudes, a turn back to the airport can be safely accomplished, provided you remain within the maximum distance published for the MSA or TAA.
Okay. Before takeoff checks, please.
Now that we've reviewed considerations for takeoff obstacle avoidance that should be part of every pilot's pre-flight planning, let's see how this planning enters into play when the engine fails on takeoff. We join our flight crew as they receive their takeoff clearance from Aspen's runway 33.
Tower, November 300, Charlie is ready for takeoff.
November 300, Charlie, winds are light and variable. Altimeter 292, you're clear for takeoff, runway 33.
Clear for takeoff, runway 33, November 300, Charlie.
Finals clear.
Clear on the right. Runway heading is 328 and we are cleared for takeoff.
Firm.
Takeoff power set. Airspeeds are live. $80 knots, cross check. V1, rotate. Positive rate.
Gear up.
At the left engine roll back.
Okay. There's the end of the runway. Coming 340, heading half bank. Speed bug V2.
Set. Looking for 10.3 miles.
Copy that.
November 300, Charlie. Contact departure 123.8. Have a good day.
November 300, Charlie. Switch.
And when you get over there, go ahead and declare an emergency.
Departure November 300, Charlie is with you, declaring an emergency. 5 souls on board, 3.5 hours of fuel. We've had an engine failure. We're flying the lens departure procedure. We'll be holding at lens on the 244 with left-hand turns.
Roger, November 300, Charlie. This is departure. We acknowledge your emergency. Report entering the hold at lens.
We'll report entering the hold November 300, Charlie. There's 10.3.
I'm in the turn to 270. All right, we're looking for an acceleration height of 9,330. If you would help me watch for that.
Will do. Passing 9330.
Accelerating 170.
Nav's available. Would you like the engine failure checklist?
Engine failure after V1, affirmative.
Engine failure procedure above V1. Rotated VR pitch attitude adjust is required to achieve V2. Landing gear up after a positive rate of climb. Climb at V2 until clear of obstacles, then accelerate to V2 plus 15. Flaps retract. Then climb at en route speed. That's where we are right now. And I have the engine shutdown in-flight procedure.
Go ahead.
Thrust lever.
Confirmed?
Left
Change.
engine run switch off. Confirm.
Confirmed.
Rudder trim as required. Electrical load reduce. Bleed switch off. Cross flow open. Anti-ice off. Monitor fuel balance. Cross flow is required. Transponder goes to TA only. Land as soon as practical. Next is the engine air start procedure or the single engine landing procedure. Your choice.
We'll do the engine air start. There's no reason not to. We use the APU assisted one, so we'll get the engine restarted if we can, and we'll proceed get a clearance over to Denver as we discussed previously, and just soon not go back into Aspen.
Concur.
We will probably need to climb to at least 17 or 17,000 or flight level 190. We can ask ATC, but that shouldn't be a problem.
Roger.
And if you want to tell him we're crossing lands, entering the hold.
Approach November 300 Charlie Charlie's entering the hold. We're going to run a checklist and then proceed to Denver. We'll advise when we're ready.
Roger 300 Charlie Charlie. We mark your time entering the hold. Let us know how you wish to proceed.
As we bring the discussion to a close, it is beneficial to review a few key points. Part 121 and Part 135 operators of transport category airplanes have a legal requirement to ensure that the net takeoff flight path clears obstacles following an engine failure at or above V1 speed. These operators must consider takeoff obstacle clearance for every takeoff. It does not matter if the airplane is operated under instrument flight rules or visual flight rules, or if the weather conditions are VMC or IMC. Though not required, voluntary compliance is strongly encouraged by Part 91 operators. The climb gradient requirement, published in a standard instrument departure or an obstacle departure procedure, assumes normal all engines operating performance. Demonstrating that the airplane can meet these climb requirements after an engine failure is not required. If the engine fails on takeoff at or above V1 speed, fly the engine failure procedure. The SID or the takeoff climb-out instructions received from ATC are no longer applicable. Advise ATC of your intentions when it is safe to do so. As we have seen in the presentation, the determination that safe takeoff obstacle clearance can be achieved following an engine failure on takeoff is not an easy task. Ask yourself, is this assessment something that I can perform before each takeoff? Do I possess the training, the tools, and the skills to analyze the engine out performance of my airplane? Can I determine where all the critical obstacles are along my takeoff path? Can I calculate a takeoff weight that will clear these? An engine failure is an extremely rare event with today's modern engines. In fact, many pilots will never experience an engine failure during their career. However, a study of accidents and incidents occurring between 1959 and 1996 involving engine thrust problems, including engine failure, found that over 70% of these events occur in the takeoff and climb phase of flight. If you should be one of the unfortunate few who experiences an engine failure on takeoff, will you be prepared? Will your airplane have the necessary performance to clear the trees, buildings, cell towers, and the terrain beyond the end of the runway? Performance planning is key if a pilot is to meet these challenges.